Daniel is a professor of artificial intelligence at the University of Hertfordshire, is well known in the ALIFE community, so will be interesting now to hear a kind of more ALIFE perspective on things, on what insights from ALIFE can contribute to AI alignment. So yeah, over to you, Daniel.
Hello, can you hear me? And if you can't, please let me know, because I'm speaking a bit more silently. It is 3 o'clock at night where I am. Can you hear me?
Yep, we can hear you fine. And again, yeah, thank you very much for joining at this kind of insane time in the morning.
Perfect. Okay. So I called my talk Taming the Terminator for obvious reasons. And I want to talk about ALIFE insights to put AI in its place. And in fact, it is quite striking that many of the points I'm going to talk about are actually meeting with what we heard in the previous talk. So let's just get to it right away. So I have here a slide, and don't bother reading every detail on it. Basically, it shows some major evolutionary transitions in the culture of human information processing. And most of it are just steps in communication, but I want to highlight a few, which are a little bit more than that. Roughly 70,000 to 100,000 years ago, as far as we can tell, is estimated language emerged, which is basically the first step to actually make thoughts, process them in a completely new way, as instead of some unformed, ill-defined blobs of consideration. Suddenly you can express them, they're much sharper, you can exchange them with others, and they become a communal property. Another major step is, of course, the discovery that you can actually store them permanently, in fact, for a very long time. And writing is, of course, the next step. And then there are lots of steps in the organization and communication and spreading of information. And basically now, in the last years, we have made this step where information is not only just reactively processed by non-human entities, but actually machines start actually intervening in how information is being created. I mean, what ChatGPT does is a culmination of this process, where it basically starts intervening in what type of information is actually being generated. It's not a purely reactive transmission of information. So what I would like to emphasize is essentially, if we go through all these steps here, is that we have relatively few transitions where really qualitative modification of how information is being processed happens. Most of them are just faster communication, further communication, communication to larger amounts of receivers. Very rarely it is a qualitative step. And this is one thing that we have experienced now, which is always an enticing outlook, given that most of these transitions are actually linked with major societal upheavals. But I'm not going to talk about society. I'm talking about, of course, what is the role of AI, what is going to meaning for us. So I basically would like to emphasize to the fact that when we have technology that determines content of agenda, the agent, there is an element of increased agency. It's not a reactive process anymore. It's a kind of entity that, well, to echo the previous talk, wants something. Well, that's the question. Does it want something? And that is something we're going to discuss. It's very important for what I'm going to talk about. So first of all, let us notice one thing. AI, as we have it today, the type of AI we're talking in this type of context, for example, ChatGPT and its friends, is overpowered. Overpowered is a term from games, when you have basically a skill that is completely outside of the abilities of all other players. There's no other player that can compete even approximately with that skill. that skill is basically overpowering everybody else. In which sense? It's fast. You can make it write 2 pages of new text, more or less new text, reasonably original text, from a few bullet points. You will need at least an hour to write that, even if you're an experienced writer. Number 2, it's potentially omniscient. Now, the fact that it's currently still hallucinates, it's just a matter of time until that technical problem is going to be resolved, I would say. And then in that moment, that thing beats any human Jeopardy player, blows them out of the water. There's no competition, right? It is completely laced with all information that ever was committed to an electronic medium. It can produce plausible decisions, messages, actions at any time of the day, at any volume. And of course, it isn't transparent. We have no idea how it gets to that conclusion, so it may come to very problematic conclusions. For example, imagine a legal document that you don't understand. You submit a legal document of 100 pages that was sent to you, and the system says, okay, you have to do this, 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 and you believe it or don't believe it, and you have no idea whether this is something that you can handle. With a lawyer, you can at least discuss and say, okay, what does it mean for me? And the lawyer will actually try to make a sense out of it. Sense in terms of strategy, sense in terms of what it means for you as a person, etc. So if I would like to paint this little diagram here, where we see essentially the ecosystem in which we are is a lot of individual small little entities called, little single-celled organisms. Us. Well, we are not single-celled, but essentially in terms of a volume of information that we process, we are very small. Then we have this huge homogeneous AI block that does it want something? Well, we don't know. We'll discuss that in a second. And finally, we have basically like Kilroy sitting over the wall watching this with potential vested interests, but also with some question what is actually going to happen next, because it's not really clear. We don't know what the trajectory is going to be as a further actor in this game, and it's a relatively big actor too. So I would now to come to the aspect that where ALIFE can help us analyze this. So I would like to emphasize analogies and differences to biological complex systems. What are the analogies? So first of all, we have different entities of different size, basically orders of magnitude different size. You have intransparent and difficult to trace agency. It's not clear what they want. We have seen an example with E. coli, but essentially here it's a lot of players and it's not really clear what their goals and utility values are. You have order of magnitude differences in what I call here very cheekily free information levels. So when I talk about free information, don't think of it as a well-defined term at this stage. It's more a kind of the analogy to chemical free energy in processing of work. When you want to generate work, you need chemical free energy. And this chemical free energy is something that allows you to work. And this free information is basically the amount of usable information processing capacity. I think David Volpert has a related term to that. Essentially, how much capacity you have that's not just metabolic, but allows you to actually process information in a kind of way, and it's much more available to this machine than to us. It can process much more complex data in terms of amounts. Not necessarily better. I'm not saying that, but it has a vast increased bandwidth. And the whole system here has many agents with uncertain agendas. Many agents means not just this machine, but also humans that try to trick the machine. And it's possible to trick it. I have tricked it, not with indirect questions, but actually by going to a different language. So I have actually asked a question that it didn't want to answer in English. Then I went to another language, and it did answer it actually quite impressively. But it was certainly something that worked because that language did not have as many sensors available. Now, what's the difference to biological complex systems? So here, basically, if you look at this AI, it's a huge, relatively homogeneous blob with little real internal structure. Of course, it's a network, and the network has weights, and they have learned, but there's no grown organic evolutionary basis for how it got to that size. It basically was engineered to do this job. So everything is packed into the system, and it learns it using these rules. Maybe there's an internal structure that we don't really fully understand. Certainly must be some structure, otherwise it couldn't do what it can do. But essentially, we don't see these different levels of evolutionary history reflect there. And I do think that changes a lot how that system operates and how we have to look at it. It does not have to battle with bow tie parasitism. So what's bow tie parasitism? This is actually an idea that I think was first, actually, I heard it first from John Doyle from Caltech, and basically a bow tie as an interface that is very, very universal. Think of ATP for energy transport. That is a bow tie, or the internet protocol for communicating, having different computers communicate. And bow ties have the big advantage that they are completely universal. Everything can communicate with everything. But the price to pay is that this bow tie is a very attractive loot for parasites. So they want to attack it, and therefore bow ties need to be protected by heavy, massive networks. Both ATP, the ATP cycle is protected by a lot of protected networks. When the internet, you have all these layers of security to protect the safety and the integrity of transactions. So this is what I mean. And this AI does not so much have to battle with that, because that job is done by a whole horde of human sensors. They do this job, but this is not really bow tie protection architecture. Is externally imposed on the system, is engineered into the system. It's not organically grown. And finally, the AI does not have an articulated agenda, at least not yet. Even if the companies do have, but as we say, this AI is a proto-agent. It's not really something that wants something concrete. Maybe at some point it will try to sell us stuff. At this stage, that's not still something. And if it wants to sell us stuff, this is hard-coded by the companies. So what are the ALIFE lessons here? And I try to highlight there some things that are similar, some things that are very different. So we want to learn lessons about the relation between AI and society, what tools to use to analyze that, and finally, can we use ALIFE principles to preempt problems before they occur and not after the damage is done? So in ALIFE, we know a lot of things about parasitism, about evolution, about evolutionary races, about extinction, about basically ecological niches, Cambrian explosions, Permian culling. And the question is, can we learn something from there to talk about what this means for us? So I will try to give an attempt at answers. So ALIFE studies is a very special type of complex systems. It's a subset of complex systems. Complex systems is bigger. The ALIFE talks essentially about systems that have components with agency. You could also demand evolution, but I want to make it as general as I can. I think let's talk about agency. I think that's a good approximation to talk about when I talk about AI. And modern AI has begun to move beyond pure instrumental activity. So when you have optical character recognition, or you have speech recognition, or you have grammar repair, or things like that, this is AI already, but they are reactive. They don't really invent something. They really try to reproduce faithfully what you're doing. Now it's changing, right? You have this machine that can actually has a certain degree of its own generation. I mean, it doesn't matter that Shakespeare may have written the original text, or some famous author has added this text to the machine, but the machine picks it, combines it with other things to get something moderately original. So when we want to look at the interaction of things, then in ALIFE, we look at networks of living organisms, and they have an agenda of their own. Again, we come back to the concept of agenda. They have a range of operation of their own, and they live in vastly different niches. So one thing that we have to think about is when you have such an AI, the first thing you need to do is to socialize it. Make clear that it lives not in a vacuum. It lives in a social context. Social doesn't mean it's just social amongst humans, but social amongst other AIs, other companies, other entities that have their own agenda. And so socialization is, I think, a very important issue. So assume that the members of above networks are endowed with agency. This is now, I take purely the agency standpoint. It is not an exclusive thing, but this is my approximation. Now, the job of the biofilm, this is a society, if you like, but it's more general than that. The biofilm is where it's embedded, is to socialize other agents so that they don't basically overpower the biofilm. And it becomes actually more difficult with AIs rather than other organisms because the AIs have no natural survival necessity, and therefore they have no instinct. You can't scare them that you could kill them. If they are going for one route, they just do it, right? It's like, sorry to say, stupid people. They may actually not have natural survival instinct at this point. So we are going to do a case study about modeling this with intrinsic motivation. And those who know me will not be surprised that I'm going to use empowerment, but this is clearly not the only way to do that. Now, before I continue, how much time do I have left? Just to make sure that I don't exceed my time.
Yeah, I would say you have another 5 minutes or so, and then we'll have a bit of time.
5 minutes.
Yep.
Okay. Right. So basically, empowerment is a measure, is a quantitative measure. I want to be quantitative now, not just on the high level, that you want to be in control of your destiny. And an agent wants to control its own destiny, and it needs to know that. And to do so, basically, you can quantify that by taking an agent. This is the world. This is, well, let's skip this part here. So this is the world. This is a sensor. This is an actuator. The actuator impinges on the world. Together with the previous world state, there's a new world state and a sensor output. And as you do something, basically what you measure is, I act on the world. I let the world pass one step. I act on the world again. I let the world pass a step. I act on the world, and I read out what happened. And I look at the effect that my actions had on the observation. So I do something to the world, and then I find out that it had an effect. And I measure this, and I maximize this effect. This maximization gives me a value that can be actually, when these are all random variables, measured in using neutral information. So you measure the neutral information between the actions and the outcoming sensor state. And this thing depends on the starting state and is called empowerment. Empowerment is a measure, if you like, for the agency of this agent. How much agency does this agent have? Can it do a lot? Can it do a little? Right. I'll skip the motivation. Just run with me and believe me that this is something that works. Perhaps the best motivation is money. Money is the potential of doing something. You can change things having money. You have the potential to do that. Doesn't mean that you do something. It just means that you have the potential, and the postulate is you go to states of maximum empowerment. So I want now to talk about the socialization aspect. So when we talk about empowerment, we have talked about our power. But now, if you want to make altruistic agents, for example, think of an agent that is intelligent but wants to help humans in the sense of the 3 laws of robotics. But the 3 laws of robotics are somehow flawed for various reasons. So let's ask the different questions. So I have this diagram again. This looks very complicated, but actually it's quite straightforward. So essentially there are 3 types of empowerment here. Here we have a human. Here we have a robot. And what we want is that the robot does things that maximize the empowerment of the human. So the robot does things that make the life for the human easier. It doesn't just protect the human from harm. It makes sure that the human can do whatever they want to the highest level they want. Think of it like a robotic butler, something that brings you all the tools you need, ideally before you even call them, because they know already how you're working. So you are always ready at your maximum potential. So this is basically the first rule. The second rule is basically make sure that the robot is close to the human and is always available to help. And how do you do that? Well, we can measure the human-robot empowerment. How much influence does the human have through what the robot is doing? And that means that the robot is basically following the human's commands. This is analogy to the second law. It's not exactly the second law, it's slightly different. It makes sure, however, the robot tries to be close to the human and help the human achieve their goal. And the third law has also an analogy in this picture, and the analogy is essentially to maintain robot empowerment. The robot needs to maintain its own empowerment, and empowerment is a proxy for survival. So if you have high empowerment, it means that you're far away, or you have a good likelihood to survive further because you have lots of options ahead of you. If empowerment goes to zero, it means you're close to death or you're dead as an agent. So you try to stay away from it. And so you can model them, you can weigh them differently. And when you do that, you get robots that actually follow humans. You get, this is a longer story where the robot actually in the balance of this game here, basically the robot goes out of the way from the enemy. The enemy is red, the robot is blue here, goes out of the way to not be shot by him, while this robot shoots the human. The reason why the robot does not help the human here is because the human has much more health than the robot. The robot correctly infers that it needs to survive to be of use to the human, and first gets out of danger, then shoots the robot, the enemy endangering the human, and only then it basically the shooting of the enemy robot happens only after it went out of the way of its own danger. And that weighting can happen automatically by the fact that the robot predicts, it has a forward model, predicts what will happen. So we have an interesting ethical dilemma. Should it help the human first, or should it get out of danger first? Get this human dilemma neatly modeled in this Lagrangian fashion. I finally want to close with the nasty side of this. You can, of course, do antagonistic empowerment. This is a wonderful work by Christian Guckelsberger and Christoph Salge. And here you actually program the robots to do antagonistic empowerment. They try to reduce the empowerment of the human. And they can also reduce these three types of empowerment in different ways. And you get different type of psychotic behavior. So in one case, you get what I call the cowardly backstabber, the robot that tries to kill the human, but only if it doesn't harm them or if they are safe. Then the psycho killer, the robot that always tries to kill the human no matter what. And the third case, which they call supervillain, basically Bond supervillain, throws the human into lava. And just before the human dies, they pull them out and heal them so they can throw them into the lava again. Basically, they try to prolong the power over humans. Yes, this came out. This was emergent in this model. So we really, first of all, the interesting part is we recognize natural behavior. Second part is this teaches us something, that this type of look at this type of decision-making can help us understand what can we expect from a plausible AI, what type of dangers, and how we can start thinking about mitigating that. Thank you very much.